Good morning, everyone. My name is Zhang. My advisor is Professor Zhang. Today my presentation is about Chiral Symmetry breaking and deracemization of sodium chlorate in Couette-Taylor Crystallizer. And this is the content for my today's presentation. It will include these four parts. Firstly, what is chiral enmeshment? Chiral enmeshment are non-superinflexible mirror images, such as these two figures. They have almost identical physical properties, but different chemical behaviors in an asymmetrical environment, such as human bodies. And as shown in these figures, the enantiomers interact differently with chiral receptors. One of the enantiomer could be recognized and be accepted as a receptor. However, another enantiomer could be rejected. So there are many examples of chiral drugs shows different activities with different enantiomers, such as the thalidomide. The R enantiomer of these drugs is a good sedative. However, the S enantiomer of these drugs have a bad effect of teratogen. So chiral isolation is very important for pharmaceutical industry. And chiral symmetry is synthesizes two enantiomers with equal fraction. Like most of the industry products, it needs further separation to get pure enantiomers. And chiral symmetry breaking, it is a process produce a single enantiomer or larger to make a large X size or one of the two enantiomers. And for chiral symmetry breaking, one of the landmark studies for chiral symmetry breaking is studied by Couette-Taylor et al. They studied the evaporation crystallization with additive effect. As shown in these figures, in a no-stirring condition, the chiral form of L and D was almost equal in the final result. However, in a stirring condition, there was interesting to find that there was always only pure L or pure D form crystals in the final state, and it indicated that the fluid motion may promoted for chiral symmetry breaking and deracemization. And so why we use the Taylor vortex flow? Taylor vortex flow is the periodic Taylor vortex flow generated in the gap of two cylinders, the stationary outer cylinder and the rotating inner cylinder. This is a homogeneous fluid motion with excellent mixing effect. And this kind of Taylor vortex flow has already widely applied for crystallization, such as for control morphology and size distribution, or used to promoting polymorphic nucleation and phase transformation. And this is the experiment set up of Couette-Taylor. We call it CT crystallizer. And for comparing the same experiment was also conducted in the mixing tank we call the empty crystallizer, which will generate a randomly turbulent eddy flow. And in this study, the sodium chlorate is used as the model materials because it is an air chiral molecule in the solution phase. However, it crystallized to chiral crystals in a solid phase. So in the chirality of sodium chlorate crystals can be distinguished using the polarized microscope. As shown in these figures, the color difference indicated the different chirality of crystals, and the crystal enantiomer axis CEE here is divided by this equation. Here the NL and LD is the number of crystals in each sample. Now let's move to the result in CT crystallizer. Here shows the effect of the rotation speed during cooling crystallization. As you can see in this figure, here, firstly, the CE achieved at the induction point we checked as initial CE. Here, at a raw rotation speed of 100 rpm, we can find that about 50% of CE was achieved. However, the initial CE increased to about 80% when rotation speed increased to 700 rpm. And so the deracemization was also increased in this process. So in all of this experiment, 100% of CE was achieved except 100 rpm. figures, when increased the rotation speed, the CE at induction point increased, and also the induction temperature also increased with increasing rotation speed. And we also calculated from the induction temperature, we find that the supersaturation decreased in this condition with increasing rotation speed. And this is the crystal size change as different rotation speed during this cooling crystallization. We found that when the rotation speed is higher than 100 rpm, here, firstly, we call the crystals finally in exercise as the major form, and the crystal, another one is as the minor form. We found that when the rotation speed was higher than 100 rpm, the minor form crystals finally decreased to 0. This is due to the complementary deracemization of minor form to major form. And when the rotation speed is 100 rpm, both of the minor form and major form crystal size increased together. And at the same time, we also studied the effect of cooling rate during this experiment. And we found that at a high cooling rate of 0.295 degrees per minute, the initial CE is about 60%. However, this initial CE increased to about 90% when the cooling rate decreased to about 0.074 degree per minute. And the deracemization also enhanced with decrease of cooling rate. So complete deracemization means 100% of CE increased in all of these experiments. So as summarized in these figures, when decreasing the cooling rate, the CE at induction point increased and the induction temperature increased too. So correspondingly, the supersaturation decreased in this case. And here is the crystal size change as different cooling rate. Because of the complete deracemization, all of the minor form crystal size finally decreased to 0 micrometer. And we also compared the experiment result in CT crystallizer to that in MT crystallizer. And it is very interesting to find that in MT, here, in CT crystallizer, all of the deracemization reached to 100% except in 100 rpm. However, in MT crystallizer, only when the rotation speed is 1000 rpm, we achieved 100% of CE. However, in other cases, the initial CE just slightly increased and then it kept at a constant value without further evolution. And here, it is important to mention that is the initial CE in both MT and CT increased with increasing rotation speed. However, the initial CE in CT is much higher than that in MT crystallizer. And the same result was found in this condition when varying the cooling rate. So what is the mechanism behind this chiral symmetry breaking? According to the classical nucleation theory, the nucleation rate is closely related to the supersaturation S, and the time interval between nucleation of two crystals here we define as 1 divide the square of known S was inversely proportional to nucleation rate. So here we make a figure about the nucleation time interval between nucleation and the non-initial CE. And we found that when decreasing the supersaturation, the time interval between nucleation of two crystals increased. So the initial CE increased. This is because a longer time interval between nucleation of two crystals, it will lead to longer time for crystal growth and secondary nucleation. Here, the secondary nucleation will bring more crystals with the same chirality to the mother crystals. So this will result to a larger initial CE, we mean the higher initial CE. For a summary, 100% of CE was achieved for all the experiments in CT except in 100 rpm, and the initial chiral symmetry breaking was enhanced by increasing rotation speed and decreasing cooling rate. And the Following relations of initial chiral symmetry breaking with the induction supersolution suggesting that secondary nucleation played a key role in chiral symmetry breaking. And the initial chiral symmetry breaking was produced in CT crystallizer than in MT crystallizer, as the Taylor vortex flow was much highly effective for secondary nucleation. This is all of my presentation. Thank you very much.